Researcher Fellowship from the Ministry of University of Italy in 2008, Erasmus Mundus Fellowship for 34 months from European Union in 2010, first prize as a student team leader of the University of Padova in class 3 of Formula Electric and Hybrid in 2011, 2016 Best Paper Award of IEEE Transactions on Industrial Electronics, and Visweswara Young Faculty Research Fellowship for 5 years in 2017. His research interests include power electronics and electric drives for electric vehicle propulsion and charging infrastructure. He is associated with IEEE, IES, and PELS and contributed as chair for technical track and special session in ICON 2013 to 2019. He has contributed to a technical committee on transportation electrification of Industrial Electronics Society (TCTE) IEEE as conference activity chair from 2017 to 2018, secretary from 2018 to 2019, vice chair from 2019 to 2020, and chair from 2020 to 2021 of TCTE. This was a small introduction of Professor Keshri. Now I request Professor Ritesh Keshri to throw a light on the said topic. Thank you and over to you, sir.
Thank you, Rasmi. Please let me share my screen. I hope you are able to see my screen
Not
No,
visible,
sir.
sir.
Now
Yes,
now.
visible.
sir, it is visible.
Yes, yes.
Small screen.
So, Rasmi, because this is my second session. Uh, in the first session, I started discussing about an introduction of the electric vehicle system, and then after we try to understand what are the different components of the electric vehicle system, and then we talk about the traction system, the candidates which are there for the traction motor, like PMBDC motor are there, permanent magnet solutions and non-permanent magnet solutions are there. Then synchronous and asynchronous machines. All these discussions we have carried out, and then we have discussed a bit about PMBLDC motor drive. Okay. I try to explain everyone that what actually is a PMBLDC motor. So it is a synchronous motor in which a rotor is replaced by a permanent magnet and stator winding is concentrated in nature. So this I explained. Then I was explaining about different classifications. Okay. Then I explained about what are the surface mounted permanent magnet machine, what is interior permanent magnet machine, what is the difference between them. Then after we discussed about like further classification as per the electrical structure, 180-degree arc magnet, 120-degree arc magnet. In one case, we see that in 180-degree arc magnet, star connected winding is used. In 120-degree arc magnet, delta connected winding is used. Okay, this I explained. Then I explained about PWC motor and its equivalent electrical representation. That is, it can be represented by a three-phase RLE load in which back EMF is trapezoidal in nature. And then I explained that what is the requirement for a PMBLDC motor to produce a maximum torque per ampere, because the current is trapezoidal, back EMF is trapezoidal in nature. So we have to inject the current which is synchronized with the flat top portion of the back EMF, this portion. Okay, this was required. So then only we will be able to produce maximum torque per ampere. So this I explained to everyone. And so these are the back EMFs and phase currents for the three phases. And then I explained that how actually this PMBLDC motor works, means how we can make it rotating. So this I explained with the help of this basic concept of electromagnets. And these things we have discussed, like we need to inject the current in proper sequence, then only so that we can let this stator flux, here you see, this is stator flux to this one, to move further so that the rotor flux, what it is there, it will catch it. So this we discussed in quite detail during our last discussion. So you can see that as we change on the current injection, then this stator flux phi s, what you see, this is changing and this is moving further. And so each time this rotor flux phi r try to catch it and get aligned with the phi s. And so you can see that here that we are changing IB plus IC minus. So that sequence is changing, and that's why we are able to make the motor to rotate. So these things we have discussed. And then the question was that like we have a stator back EMF. So now I'm just continuing. So I will not take much time for this discussion because we have to also discuss about something about the charging infrastructure. So that part also I will be explaining you. So let me complete this section of BLDC motor in brief, and then we will move to charging infrastructure. So here you see that as I explained you earlier, that the back EMF of a motor, of a BLDC motor is trapezoidal in nature. Okay, this is trapezoidal in nature. Here you can see. So what we need to do, that our requirement is that we have to inject a current which is synchronized with the flat top portion of the back EMF. So, but we don't know where the rotor is at present and how we can get the information of the rotor position. You see that these are the electrical angular position. So to know the angular position, we have Hall sensors with the motor. You can see this one, and this one. These Hall sensors are what? If you remember that I have shown you the photographs, some pictures here. You can see these pictures. These are the Hall sensors. Let me make it zoom. So these are the Hall sensors which are placed on the stator of the motor. Okay. And this is placed in mechanical space. This also I explained that how it is appearing like around 15 degree uh, mechanical space, but it is actually in electrical space, it is 120 degree because there are 16 pole pairs. 8 pole pairs are there. Okay. Let me go there again. So to know the rotor position, in case of BLDC motor, we use Hall sensor. And what it do, Hall sensor? So please, you remember that this first thing is that these Hall sensors are, you see that around 15 degree, this one, this is ahead of this one, ahead of a particular phase. Hall A is, phase A is this, so this one is ahead of this one. And how the motor is rotating? This is rotating like this. So first your Hall sensor is going to come and then your phase will come. And you can see here, our rotor is placed, rotor is what? Remember that it was 180-degree arc magnet. Means rotor is something like this. Okay. This was 180-degree arc magnet. Okay. So let us consider this is south pole and this is north pole of that 180-degree arc going. So whenever this south pole approaches Hall A, in that case, this Hall A will become high. And whenever the north pole will approach Hall A, it will become low. Okay. And the duration is what? What is the duration of this magnet? It is 180-degree arc magnet. How many magnets are there? Two. So electrical angle and mechanical angle is going to same at present. You can consider here because we are taking this example. Now let me bring you this case how it is working. So let us consider uh, uh, make a diagram in which my intention is to show you that how these Hall sensors are getting high or low. Second case, and this is third case. So let us consider that Hall is placed here. Let's say this is Hall sensor A. And now what is happening that this one is our south pole. Okay, this is our south pole, and this one is no upper one is north pole. Is not so. And what we are doing, we are rotating our motor. Okay, so you see that this south pole is approaching Hall A. So in this case, at this particular position, you will find that the Hall becomes high. Okay, here Hall becomes high because it is approaching it. Now, here you see that another position we are drawing in which this is the question. This is the midway situation. This is your south pole and this is your north pole. Okay, Hall is here. So the voltage which is going to appear with this Hall A, it will be minimum here, but the maximum here. But in any case, let me draw first a flat portion. So in this case, we are at maximum position. We are keeping it to rotate. Now, third possibility is what? You see, so it will continue to remain. Then this third case, what we are drawing is now the south pole is going to, north pole is going to approach Hall A. This is north pole and this is south pole. This is north, no? Okay. And here is our Hall. So when this position arises, you see that our Hall A output is going to get reset. It was earlier high here. Okay, this is Hall A. This is 0 degree, and this is your 180 degree. And then again, this process will continue. So this will remain low. This will remain low because it is now in the vicinity of North Pole. So this Hall output will remain. Hall output means you are trying to observe this output here. Okay, let's say B Hall A. Okay, this is output. So this will remain low again for next 180 degree. Why? Because it is in the vicinity of South Pole. No, sorry, North Pole. Okay. So then let us consider that 2 pi is here. So this is the nature what we actually observe. But in practice, you will not see this one. Here you will have the minimum voltage, and then gradually it is going to be maximum at this position. Why? Because maximum flux is getting linked here. Then again it will get down, and then it will get reset low. And again, next time the cycle will come, it will become high. So means the actual Hall output, what you will be seeing is something like this. Like this means, but with this information, it will not be possible to work properly. Okay, so what we do that we have to make it in a square wave with the edge detection circuits, which you can use with the help of op-amps also. So what we do that we make it high here like this with the help of edge detection circuit. Wherever it is greater than 0, it remains high. The moment it becomes 0, we get like this also. Okay, so similar same thing is going to happen with Hall B, Hall C, like this. Okay, so these are our Hall A output. Now let me go back. So now you see that same thing is happening with the 3 pages, the other halls, Hall B and Hall C. So that's why we see that this is the, you see that here we are having Hall A positive, and then Hall B is there and Hall C is there. And they all are displaced from each other by 120 degree. 120 degree. Then this one is also 120 degree. Now, so how this helps us in knowing the information of the rotor position? So please see that we are having 6 different combinations. This is 1, this one is 0, 1, 1, 0, 0. 1 1 0 0 1 0 0 1 1, then 0 0 1, and the next it continues here. So this is what it is shown on this side, 0 0 1. So these six are 1 2 3 4 5 and 6. These are six different Hall states we are observing. So now we have to see that what is the relationship with the current, because we have to actually inject the current by turning on upper or lower switches of a particular leg. So what was the requirement of the current? You remember that we need to inject the current like this here. We need to inject current like this one. So please see that where we have to inject the current, where the positive Hall, positive flat portion of the back EMF is starting. Okay, and where we have to positive current, okay, plus I, and where the negative current is getting injected, where the negative flat portion of the back EMF is starting. So we have to find the relationship. So please see that this is the instant where the Hall A is getting high. You see that positive flat portion of the back EMF is starting, and up till how much it remains high, where the negative flat portion of the back EMF is starting. So 180-degree complete. So we can say that suppose that we have a Hall state 101. So where we are, here you see that IA is positive, and see that yellow one EB is there. So EB will be negative. Why? Because the EB back EMF yellow one is okay like this. Okay. This is EB. This is the case of EB. Similarly for EC, you see that this is EC. So we can make it a bit thicker one. Okay, EC. So from here you see that we are getting some information. We are getting some information what the current. So sorry, this is not this one. Huh? So all the phase currents are appearing here. You see, okay. So this was IA. This is IB, and this one is IC. So you can say that when Hall 101 is there, so IA is positive, IC is 0, and IB is negative. So IA positive, how we can make? We can make IA positive. This, you remember that last time I have drawn this diagram for the inverter, three-phase voltage source inverter, and the switches were what? 1, 3, 5, 2, 4, and 6. So this was, you see, this was the situation. This is A, B, and C. So IA positive means we have to turn on switch 1. Okay, then only we can make IA positive. Okay, then IB negative means what? This was negative now. So the current should pass through the switch, like in the current. You see that this is IB. Entering current is considered positive. Like here you see, let me draw here. So this one, and this one. So this is IA, this is IB, and this one is IC. A, B, and C. So if current is entering into the motor, it is positive, and the current, if it is exiting outside, then it is negative. So what is happening? You see that current is exiting. This is reverse direction, negative. So you see that this is the situation. So when we want to realize this one, we have to operate switch 1 and switch 6. So by this way, we can say that, okay, now if you want to inject the current in this way, then we have to make the maximum torque per ampere have IA should be positive and IB should be negative. Why? Because the positive flat portion of EA is there, the negative flat portion of the EB is there. That's why. Okay. So this is a way like how we identify the rotor position of the motor, and then we select the switches to operate our inverter, voltage source inverter. Let me go to the next slide. So this is the key term. So here you see that, and because you see that the current which are injected here, this is what of how much duration? 120-degree duration. Okay. This is flat portion is 120-degree. This I explained you. 120-degree. This is 120-degree. So 120-degree mode of operation of a voltage source inverter is used for this. So simply We start from any of the houses, and let's say this one from here we are starting. This one where the positive flat portion of the vacuum is starting. This one, see where the positive flat portion of the vacuum is starting here. Okay, here you see. So here we consider that first the switch T1 is operated, then after 60 degree T2 will be operated. Why we are doing so? Because total six switches are there. So they will be operated in the sequence of a delay of 60 degree, 360 degree divided by 6. So you see T1 after 60 degree T2 will be turned on, after 60 degree T3 will be, then after 60 T4, T5 and T6. Okay. So this is what it was for 120 degree mode of operation. And once they are turned on, they remain high for 120 degree duration. So this we have studied when we studied power electronics. Okay. And operation of the voltage source inverter. So you see that inverter is operated for 120 degree mode of operation. So now you see when the T1 is on means what? Upper switch is on. So I is positive. T6 is on means what? Lower switch is operated. Let me here I can draw just to show you that what are the switches. Below I'm drawing. Huh? See, this is 1, this is 3, 5, 2, 4, and 6. These are terminal A, B, and C. So we can take it out. B, we can take it, and then C like this. Okay. So this is A, B, and C. So when we say IA positive, IA, and IB negative, 1 and 6 is operated. Okay. Then you can see here what are the switches operated. This is 1 and 6. So 6 and 1. Then which one is operated? 1 and 2. Then 2 and 3. Then 3 and 4. Then 4 and 5. Then 5 and 6. These are the switches which are operated. So as per the uh, hall position, we got to know that what are the switches to be selected. And so with our code or with algorithms, we select these switches whenever we find that, okay, hall state is 10161, 100, 12, 11023, like this we do. So when you do like this, it is possible, like we ensure that square wave current is injected and synchronized with the flat top portion of the back here. Anyone is having any doubt, you can ask me right now. Okay, then torque speed characteristic, this I explained. Now let me go directly to that control portion. We will not discuss this now because we have to discuss about the charging also. Okay, so how we basically control them? So you see, let me draw one diagram. So one of the method to control the VLDC motor is DC link current control. In this, what we do, let me draw again a diagram so that I can explain you in a better way. So if you see here, let us consider that here we are having an inverter. I should not draw this one. Just okay. Okay. Star connected winding. This is phase B. This is phase C. And here we have battery pack. Anti-parallel diodes are there. this is switch number 1, this is 3, this is 5, this is 2, this is 4, and this is 6. Now, so in DC link current control, what actually our intention? We have a trapezoidal back EMF and we need to inject a square wave current into it. Square wave current into it. Let's say that this is EA, this is EA, and the current which is injected is IA. So this IA should be a square wave in nature. And similarly for other phases, EB and EC. So what we do, basically, you remember that we operate with 120-degree mode of operation because the flat top duration is of 120 degree and we have to inject a current of 120 duration. So what we do, that injection requirement is what? This IA should be synchronized with EA, IB should be synchronized with EP, and IC should be synchronized with EC. So, and what is happening? Let us consider that mode 6 and 1 is in operation. Means 6 is what? B. So IB minus was there and IA positive is there, or IB minus is there and IA plus. This is the situation. So how it is there? It works. So you see that here, because switch 1 is on and switch 6 is on. So please let me draw the path. So when switch 1 is on, so this terminal will get connected with BDC. Okay, so this is the path. Okay, this one and this one is there. So please see here that as only two phases are conducting, so whatever the current IA is there, that is going to return here. So IB is equal to minus IA. Okay, because node is there and IC is equal to 0 because this is not conducting. So IA plus IB equal to 0 at this node. So IB equal to minus A. Now please see that one. If we control this DC link current, sense this DC link current, let's say this is IDC link current. So this DC link current is here. Whatever the DC link current is there, same current is passing through the phase A and phase B and then coming out completed path. So indirectly, if we control this DC link current, then if we control the DC link current, so indirectly we will be able to control IA and IB. Okay, so this is what is a DC link control. So in this, what we do that we set some reference here, IDC reference, and then we compare it with IDC with feedback what we take, and then a PI controller is there, the current controller, and then duty ratio limiter is there, duty limiter is there. So it will be 0 to 1 maximum, and then this generates a delta reference. Okay, this delta reference is compared with our carrier signal. Okay, 0, this is 1. And so this gives us output delta PWM. Okay, this is delta PWM. Now, what we do, this is delta PWM is known to us. So what we are doing, we have selected switch 1 and 6 and 1. Done. So once the switch is selected, then we can modulate either of the switch. So let us consider that we are modulating upper switch whenever its turn is coming, and we leave the lower switch high, is on. So when you do like this, upper switch is modulated. What is the voltage of this point? A with respect to negative terminal of the battery. EAO, that is going to be equal to delta EDC. Delta I'm writing, delta is delta PWM. Okay, delta equal to delta PWM, PDC. And what is the voltage of this point? This is VBO. Okay, this is B, that is equal to 0. So what is the voltage here? This voltage. And so what is the line voltage you are applying? VAB is equal to delta PDC. And see, this voltage will be equally distributed. So the delta VDC by 2 will appear here, and delta VDC by 2 will appear. Okay. So this is the way like how we do it. So what do you see that in this is we apply delta VDC by 2. So what is this voltage? Maximum voltage is VDC. Let me write here VDC by 2, and this one is minus VDC by 2. So thing is that why we are modulating. If you don't modulate, your motor will run at constant speed. But if you want to modulate, it means run at variable speed, then you will have to modulate it. So for that purpose, we do the modulation. And now you see that we do like this. The voltages which are there, they are modulated. Okay. And here, again, this is modulated. Hmm? This is a way. And so average value of this now voltage will be what? Delta VDC. So let's say that average is coming here, this line. This is the average line, average voltage line. So this is our delta VDC by 2. Let's say that this is our average line of this PWM modulation. So minus delta VDC by 2. So this is a way like how we apply the voltage across these switches so that the current can be controlled. Okay, you see, current will be controlled here. Means if you do like that, it will be possible that we will be able to make the current control like this. Okay. This is actually, we need to make the current control so that we can ensure maximum torque per ampere. Let me draw it very fast. Like this. Okay. So we are able to ensure that current control, and this is synchronized with the flat top portion of the back EMF. Synchronized with the flat top portion. So how this receiving current control is carried out. Let me go ahead. Then likewise, we can do phase current control also. If you want, you can control the individual phases directly. Means, like here, you see that here in this case, we have used only a DC, current sensor here. But if you want phase current control, then you will have to sense the current of phase A and phase B. Means in phase current control, we directly control the phase currents. Then what is the benefit? This, if you go for phase current control, it gives you very good performance when you run at the low speed. But during the high speed, both DC link current control and phase current control have the same performance. One thing. Second thing, if we talk about the cost, so definitely in case of phase current control, monetary cost as well as computational cost will be high in case of phase current control. But in case of DC link current control, it will not be there because we are using only single sensor. And computational burden also will not be there. Okay. Now, let me talk you about that how we actually, because you see that we have made a PI controller. So how we basically make the PI control. Okay, design this controller. This is very important. That's why I'm explaining it. So please see that. You remember that we have drawn RLE load. So this is one of the phase. And then with respect to the negative terminal of the battery, we are measuring the voltage. Terminal voltage is BAO, R, L, and EA is there. Then this is neutral point voltage. So you can, if you want, you can write on the KVL for this one. So this is rise in potential. So we can write BAO. We are moving in the direction of current. So minus IAR. Then it is minus L D IA over dt. Then it is drop in potential. So minus EA. Then again, there is a drop in potential minus PN. That is equal to 0. So we can write it as VAO minus VNO. VAO minus VNO equal to IAR plus L DIA over dt plus EA. So this VAO minus VNO, this is basically our phase voltage. VAO minus VNO. So this is written as VAN. So this is what we are seeing. It is an electrical dynamics. So we can take the Laplace transform of this. Vn equal to this one. Take the Laplace transform. So if you take the Laplace transform, what it will be? I'm writing here, VANS equal to IAS into R plus SL, IAS plus EAS. Okay. Here we are assuming that system is initially reliable. So this will become IAS R plus SL. Okay. Plus EAS. Okay. So you see that we have now this EAS we brought on this side. You see, VANS minus ES. We can write here EAS divided by R plus SL. This one is what? This whole one. This is 1 by R plus SL. Then what we have done? We have taken R out. So it becomes 1 by R plus 1 plus L by R S. And this L by R is what? Electrical time constant. That's why I have written it down. Okay. So now in the same way, then we have a motor torque Tm equal to 2Ki EA. So if you want, you can represent this arrangement in block diagram form, 1 by R like this one. So we can write it like this. Say this one. VANS plus minus EAS, and block is 1 by R plus 1 plus tau ES. This is IA. Okay. Now, then we know that the motor torque is given by Tm equal to 2Ki. Last discussion I explained you. So this can further be represented here. What? Multiplied by 2K. So that is equal to tau M, motor torque. Okay, motor torque. Then after you see that we have E equal to K omega M. So we wait for this, and the Laplace transform of ES will be equal to K omega ms. So it is mechanical speed and it's a back EMF. Now, please see the mechanical dynamics. This formula we all know that motor torque minus load torque equal to J d omega m dt d omega m. So in the similar way, what we have done here, it can be written as B plus SJ. Okay, so you can take out 1 by B. So we will have this relationship. So now you see that motor speed is omega ms Tm minus Ts TL, this one. Okay, so we can write it like this, plus minus TL load torque. Okay, TL we are writing. Then it is 1 by B plus 1 plus S mechanical time constant, where tau m is what? J by B. Tau E is what? That is L by R. Okay, then this is omega ms. Now, what is the back EMF? This is multiplied by K, vacuum constant. So we get it. This is the same way what we do for DC motor control, the same arrangement. Now, what is our intention? Our intention is that we want to make, if you want speed control, so please see that this is your motor in which you are going to give us, like generally people say about speed control. And what is the output? Mechanical speed. And this is motor model, E plant. This is overall transfer function. So if you want to have only speed control, then you have to set speed reference plus minus, compare with omega m. Okay, then you have a PI controller, and then this speed is feedback. Okay, this is what. So you have to obtain TL, set TL equal to 0, obtain the overall transfer function, and then you can work with. The most basic arrangement, which is generally used in a very low cost motor controllers available in the market. Okay, so this is a way like how we do it for the motor control. Now the question arises that this PI controller design we have to know. First thing. Now second thing is that if you don't want direct motor control, speed control, rather you are interested in current control, means torque control. So in that case, which will be the output? This IA is going to be output, and rest all these things will come into the feedback. So your representation will be like this. This is again motor model, okay, in which we are considering output current IA as a output variable. Then the input is GAN, And so we can set IA reference plus minus IA, what we are taking as a feedback, then we are having PI control. Okay, and then this. So which variable you would like to compare, you can do it. You can make the two loop control also. Basically, IA reference is what? You remember that motor torque is equal to 2K IA. So you set torque reference basically. Okay, divide by 2K, you get DC link current control reference. So IA is this, IDC, same thing. So this is the reference what you get. So, so what is GP in the second case? When we talk about the current control, this GP is, can I write here? Speed control. This GP is current control. Okay? Because these two functions will be different. This will be and different will be different. Let me go back. So we see here that this is that arrangement. You remember that I told you that like we have to take current as a feedback. So this is your the arrangement. This is your GP with current for current control. Okay. Now, when you go to design it, so we know that the transfer function of the PI control is what? This one, that is KP plus KP divided by tau I S. This is the transfer function, means output to input. So if you rearrange it, so it will become what? KP will be out, then it will remain inside tau IS. Tau IS plus 1 divided by tau IS. This is the situation. So here, and this is the like what you have seen just now. This is KP tau IS plus 1 divided by tau IS. Okay. And this one is your plant. This one. So actually what happens that you can definitely use the conventional approach, first reduce this transfer function, then you will have one transfer function, then cascade it with the PI controller, and then again you solve it, then you will have a second order representation. But that becomes quite complex and we are not that much interested. So actually what is happening, you see that we have a back EMF like this. Back EMF is like this. And you see that current what we are controlling is much faster rate than this is the way. So speed loop is that back EMF is much slower as compared to the current loop. So when such a situation arises, very happily you can neglect this one. Okay, so if you neglect this one, you can refer this for the book by Ogata. There it is clearly written for this one. So you see that we neglected, it is not there. So we have only these two parts. So you can now obtain the overall transfer function of the system, and then you get this situation, this transfer function. Okay. So now, but we always work with what? A standard form, that is S square plus twice zeta omega ns plus omega square n. So you have to bring this one in standard form. So take out this. Okay. So it will come here tau e tau I, then it is tau e tau I, and then here it will be tau e tau I. Okay. And this will not be there one. So you see that this part, what you are observing is nothing but twice zeta omega n. And this part, what you are observing, nothing but omega square n. Okay. So you can calculate your Kp and tau I parameter, that integral time constant, in terms of this known values. R is there, tau E is known to us. So what are unknown at present? Zeta and omega. Zeta is the damping ratio. Generally, we keep it around 0.8 something. Okay. And omega n is what? It is called bandwidth. Bandwidth of what? Current. And how we calculate? It is very important. Generally, people keep it 1 kilohertz, 800 to 1 kilohertz. But in practice, how we calculate it, it is important. So suppose that you please see this diagram. We want to realize this control. So what we are having a sensor. Then we are having Hall sensors. So sensing from the rotor position from the Hall sensor, sensing the current here. This one you see, current reference is set. You sense the current through the sensor. Then you have taken the controller action, okay, controller parameters. Then you have given it for the PWM generation. PWM pulses are generated. Then these are given to the driver circuitry of this switch, okay, of the switch. And switch take some time to take the action. Okay. So whatever the time lapse is there, that within that time lapse, our controller must take the action. But if you are taking the action after that one, then nothing is going to happen. So that is actually the deciding factor for the bandwidth. So this is like you see that then you can in your MATLAB you can check with your results and you will find it very less because we had a limited time. So like otherwise I would have shown you this MATLAB simulation also. Okay, so here we can get very good results. So this is of your concern, concern of our discussion at present. Proper tuning of the controller parameter plays a very important role in the performance of this BLDC motor. Okay. Just last for this one, it is not necessary that we should inject only square wave current. If you want, you can also inject sinusoidal current. But if you maintain that same RMS value for the two, the same RMS value for the two, this is current, then we can have 5% larger torque as compared to the BLDC. Okay. Same for the same RMS value, means RMS value of the square wave current and RMS value of the sinusoidal current, which is injected to the motor phase. Okay. So higher. And the another benefit is that we can have torque pulsation just 12%, 12 to 14% something, 12.5 like this one for sinusoidal current injection like this one. You see, torque pulsation. But in this case, this torque pulsation can go up to 50%. The problem here in this case, you need to work with phase current control. Okay, that increases the computational burden and the cost of the motor controller. And this is a very simple control. So somewhere something we have to compromise to get the work done. Anyone is having any doubt in this, please ask me. So that let me check that how much time I do have. Okay, I have time to talk on charging. Anyone is having any doubt, please ask me. For the time being, I'm just stopping screen sharing. Anyone? So that if no doubt is there or no question is there, then we can move on to another topic, charging infrastructure. Trust me, how much time do I have? 11:15 up till now.
Sir, till 11 o'clock, sir.
Till 11, so 30 minutes are there. So if anyone is having any question, any doubt, it can ask me, or you can type in also in chat box. So that one by one I will pick and I will answer. Okay, fine. No worry. Meanwhile, I'm just taking over to charging infrastructure. Okay. And then what I say, request that if in between you have any doubt, you can type in so that at the end we can pick one by one questions and answer that. So let me go again, share my screen again. On. Now we are having charging. Okay. So now you remember that I explained you that we have a charging infrastructure. These are things where it is this that one of the important infrastructure is charging arrangement. Why? Because we have onboard batteries, and once you run your vehicle, you discharge the battery, and you again need to charge it. So you can charge your
Sir, you are on mute.
sorry. Now, just one more. Just I want to show you. Forget about what it is written there in the slide. This one. So when we talk about the charging, huh, this is just I presented in India Smart Utility Forum week. So when we talk about the charging infrastructure, so basically what actually is the charging? Charging is the process by which we force the current into the battery so that the battery can be charged. So why we are saying charging? Because the most basic arrangement of a charger, I'm sorry, battery is what? It's an RC equivalent circuit. So when you force the current into the battery, basically you're trying to charge that equivalent capacitance. So that's why we are saying that we are charging the battery. So basically charging is a process by which we push the current into the battery. Okay. So it can be conductive charging or it can be a wireless charging. So this is. So let me go again back to my actual slide. So there I will explain you. Please remember that in the charging infrastructure also, we need to work with multiple sources, which can be like combinations. Like our charging station can be fuel cell fed, PV fed, battery energy storage assisted. So all these combinational purpose are the same requirements as they were having during the this onboard vehicles. Like you want to assist during the acceleration your vehicle through power sources. You want to run your vehicle to a energy source. So same situation is here also. You can have a charging station which can have hydrogen fuel cells, miss hydrogen storage, and then you get the energy from the fuel cell. Okay, and when you are connecting your vehicle to get charged, because immediately you are loading your charging station, so there's a possibility of drop in the bus voltage, because one could be like the capability of the charging station is limited, or maybe that charging station is for the 10 number of vehicles and you are the 10th number, and so already it is loaded. Okay, so miss, it is almost you are going to load the grid, that charging station to 80% or 90% something. So at that time drop will be taking place, so you need to have the support of battery energy storage system or ultra capacitor system or flywheel, what I explained you last time. Same arrangement is there. So let me go to the directly uh, charging infrastructure. Yeah. So this battery pack, what we say is here, you can say that this is a battery. Let's for an example, this is a battery pack. Okay. And we have some circuital arrangement. Let's say that this is AC to DC. And here we have a grid point. So by this circuital arrangement, which is a power electronics, we try to push the current into the battery pack. This is I battery. And how it is the most basic arrangement is there. This is a capacitor. So basically, when you push the current into this one, you try to charge this equivalent capacitor. And how we calculate this equivalent capacitance? Okay, let me explain you. See, generally, what happens that you see that the capacity of the battery, what we explain in kilowatt hour or ampere hour. So what is the difference between two? This ampere hour is what? Ampere is current and this is time. Okay, so this is something you charge, but it is not actually the coulomb exact. Rather, you have to multiply with, this is in hour, no? So you have to convert it in second. multiplied by 3600. So this much of Coulomb charge battery can store into it. Ah could be 100 Ah, 200 Ah, 400 Ah battery pack, 24 Ah battery pack. It depends. Uh, Then what is the relationship with kilowatt hour? Actually, kilowatt hour is what? Nominal voltage of the battery pack multiplied by the capacity of the battery pack. So suppose that someone says that it is a 4.8 kilowatt hour battery pack, kilowatt hour battery pack. So at the terminal, then you immediately have to find what is the voltage. This is, let's say that at 48 volts. So divide this one by 48. So you will get the capacity of the battery 100 Ah. So let us consider that this 100 Ah, what we are seeing, that is represented by C, that is capacity of the battery. So the normal charging of the battery is defined by what? C by 10. Means 100 divided by 10 is ampere is what? 10 hours. Means you will be able to, your vehicle will be able to charge in 10 hours. Let's say that what we do, that we charge the battery with 2C by 10. That is, we are trying to inject 20 ampere of current. So in this case, how much time it will take? 5 hours. Okay. Likewise, we can have, let's say that 4C by 10 means 40 ampere is being injected. So 2.5 hours. 10C by 10 means 100 ampere is current being injected. So you will be able to charge your battery in 1 hour. Okay. So this 1, 2, 3, 4, 5, 10, C by 10, these are called degree of fastness of the charger. Means how at what how fast you are able to, sorry, degree of fastness for the battery. That at what rate you are going to charge it. So in this case, you are able to charge 2 times than the normal charging. This is 4 times than the normal charging. This is a 10 times for the normal charging. And what is the normal charging time? Around 10 hours. So I hope the concept of charging is fast charging is clear to you. Now let me explain you further what are the different levels of charging. So this is quite common for all. Like we have, you see that we say that level 1, level 2, level 3 charging are there. So level 1 and level 2 are generally for your home or uh, like in a society or in a common public place where you can get it. Okay. So in this, basically, these are AC chargers. Means you will have AC supply. A typical AC charger, not which is available in the market, a standard what it should be, will have an unregulated AC supply. Okay, because there's a possibility the fluctuation at the supply side that you can with the help of this is PFC. This is, let's say, that PFC rectifier. You get here, let's say 400 volt or 800 volt, depending upon, this is DC bus. Huh? This is AC bus, 400 or 800 DC bus voltage. And then here you have a DC to AC inverter, which ensures, which could be a single phase or three-phase output, that a 230 volt, let's say that single phase, huh? 230 volt, 50 hertz, regulated, okay, or regulated AC. So this is basically our AC charger. This one here to here. Means in any case, the output what you are going to see, find that is regulated one, and this was unregulated supply because you do not have control over the supply. Okay, so this is an AC charger, and now here what you do, that here onboard charger. Maybe you have a onboard battery pack with the vehicle. Sorry, onboard charger. This is there. So this onboard charger is there, which is connecting your battery pack, onboard battery pack. And this onboard charger is what? You see that what is input you are giving? AC input. This is the point where you connect your charger. Maybe just a cable is coming out from your vehicle. Maybe an a charger pack, charger is given to you by the manufacturer, but the input is AC in nature. So you connect to the terminal. So, and this onboard charger again is having PFC rectifier, then 400 volt, then here, can I make this one? Here, this one onboard charger. So in onboard charger, again, you will have a power factor correction rectifier, because here you are giving 230 volt, 50 hertz regulated supply, and the PFC, then this is, let's say, that 400 DC bus, and then here you will be having a DC to DC converter. Okay, so this is the onboard arrangement. This is onboard. What we are saying, this is on board charger, and this one is what? Off board AC charger. So when you see the stand or box, see the stand or box, a charger, what you are seeing that, and it is said that is it AC charger. So depending upon of what cost this charger is. Definitely, it could be level 1 and level 2, depending on how much power it can deliver you. But it can, if it is having both the power factor correction rectification and the arrangement for the regulated output, then it is a very good quality AC charger. But for the low cost charger, what they do that you just have the unregulated AC supply. Okay, in between you have a metering, and then finally it is giving you that same unregulated 230 volt, 50 hertz AC supply. Can I write here? Unregulated. This is unregulated. But this charger, what I'm talking about, this one, this is regulated AC supply, 230 volts. So actually, it should be like this one. So depending upon how much you are paying, so you will be getting the services. Okay, so this is level 1 and level 2 charger, which can receive energy from single phase and AC or single phase or 3-phase supply. Now, when we talk about DC fast chargers, they are generally of 50 kilowatt range, 30 kilowatt, 50 kilowatt, 100 kilowatt, 200 kilowatt, 350 kilowatt, like this. Okay, so that is not possible to accommodate that much of high with this onboard arrangement. So you have a bypass to the battery pack where that off-board everything arrangement is there. Means from this point to this point. Means AC to unregulated AC to final DC point, which is getting connected to the battery. This remains outside the vehicle, a big box. So that is your DC fast charger. Okay. If someone is having any doubt, please ask me. It is not necessary that what I'm explaining, everything you are getting. So definitely some doubt would be coming to your mind. So please ask me. Okay. Now, next is we have what are the different means of charging? We can have static charging, we can have dynamic charging. Static charging means like your vehicle and the point is stationary. You see, this is a static charging again. First one, in you have the cable connection, wire charging. Second one, you see that at the bottom one coil is there, and in the ground one coil is there, and at the top another coil is there. In the base of the vehicle, basically another coil is there. So this is inductive charging, and this lower coil is receiving energy from the grid point. So same arrangement will be there, but here you have the isolation, etc. And this link is the high frequency link. Now, dynamic charging is what? You have the charging point stationary. You see that? These coils. These are stationary, but the coil which is, and the vehicle is moving over this one. And so whenever this vehicle comes over this, it gets charged. So this is the case of a dynamic charging. Dynamic charging can also be a conductive, like in railway we see that we have a pantograph and it goes up and then it receives the energy from the grid, 25 kV voltage line. So that is also a dynamic charging, but that is conductive example. And this one arrangement, what you're seeing, this is a dynamic one. Now another arrangement you see here in this capacitive charging, what we see, this is a flash charging. When the bus stops at the charging station, pantograph comes out and get it connected here. And it receives the energy in bulk, like 350 kilowatt or even more at the charging station. Within few minutes, let's say that it stay there for 1 minute. So in 1 minute, it receives that much of charge. But battery bank cannot receive it. So which is having a dynamics to accept it? Capacitor banks, ultra capacitors. So they store first you store the energy into that one and slowly discharge to the onboard battery and the traction system. So that's a capacity charging or flash charging also people say. Let me go ahead. Types of charging are, we say that it is we can have a charging is constant current charging and then constant voltage charging. Constant voltage charging. We can have a combination of constant current and constant voltage charging. Okay. Then other chargings are pulse charging and reflex charging. Pulse charging, you charge for some time, stop the charging process, again charge. So this helps us in regulation of the voltage. And there are other issues which are related with the battery, like sulfation is there in the lead acid, quite common. So if we follow this pulse charging method, then issue of sulfation also solves out. Then similarly, reflex charging is there in which you charge for some time and then you discharge the battery for some time, not this much of time. Okay. Okay. Charge and then you discharge it for some time. Okay. So this is reflex charging, and then some rest period is there. Rest period is there. This is reflex charging. So this is good for reflex charging is good for lithium-ion battery packs. Dendrite formation, etc., are solved with this purpose. Okay. So you see that this is what I was explaining you about conductive charger. This I explained you. Supply, PFC rectifier, DC to DC converter, the battery pack. Okay. Then wireless charger. Here you can see that same arrangement. This is a PFC rectifier, boost PFC. Then another problem. One problem, like in wireless charging, we have the two coils. You see, transmitting coil and receiving coil. They are separated from each other. And how much is the distance? It could be 0 to 10, 15 centimeter, 20 centimeter. Depends. What is the D by D ratio? Theoretically, it is 0.35. D is what? Distance between the two coils. Okay. And capital D is the diameter of this tube. So by this way, you can decide that how much is the or transfer diameter, I mean distance and coil diameter should be there. Then of course, like with other design changes, etc., we can improve it. Maybe we can go for multi-layer winding. Okay, that can be done to increase the power transfer. Okay, so then I remember that I just tell you that high frequency inverter, why we need it actually. Actually, it is a air separation. So mutual inductance is weak. How to improve it? Let's say that if we are giving the AC supply, so what it is? Reactance is Xm equal to omega m. That is 2 pi F into m. So how we can improve this m? If you operate at 50 hertz, it is very low. But if we increase this frequency, so by increasing the frequency, we can improve this coupling Xm. So generally we keep the frequency from 85 to 90 kilohertz. This is the range in which if we operate, we remain in non-radiative zone of wave transfer or power transfer. If we go beyond this one, then we go into the radiative zone, which is dangerous for us. So basically what we do, that you remember that earlier we had a 400 DC was. Now this is here we convert that 400 volt into AC, but we never modulate. Okay, it is something like this. Okay, then I can make this arrangement. This is the coil and the EMF which is induced there, like this one. This is the transmitting coil and this is receiving coil. And the voltage is here what? Omega M I receiving. This is the current I receiving. This is the current I receiving. This is omega M I transmitting. Polarity is like this. Okay, this is the coil. So here what we do that we give a square wave current injection. But please remember, and this side your rest of the circuit is there, so we can just make a load like this. Uh, Please remember that what happens that only inductive transfer is not sufficient. Why? Because uh, like it has a limitation of the length. Magnetic field is there now, so it's a closed line of forces, and it is not able to travel here in this case for a much longer distance. If you keep on increasing the frequency, then it will be definitely possible. But what we do that this is H. Okay, so you remember that we have studied in our class 12 as well as during engineering education. E cross H is what? It's a flow vector. Means you have electric field like this. Okay, and then you have a magnetic field like this. Sorry, okay, let me make it like this, like this. When E and H is there, then this is like, huh? This is like this. So this wave starts traveling. It starts traveling. I can make it here. This is E and this is H. It starts traveling. So when it starts traveling, it is possible that you can extend the range. And so that's why for better coupling, we need to make between these two coils, we need to make a inductive resonant coupling. Inductive resonant coupling. And why we do so? And we do inductive resonant coupling by using proper compensation, this capacitor and this compensation. And so these compensation can be SS compensation. Okay. Means a compensating capacitor can be connected to the both sides. Or it could be, let's say that we place the capacitor in parallel. PS compensation. Okay. This is P and S. Transmitting side, parallel capacitor, receiving side, series capacitor. Then we can have parallel combination. Similarly, we can have different combinations of this compensating capacitor. Some cases the range will be more, some cases range will be less, in some cases voltage stress on the capacitor will be more, in some cases current stress on the inductor will be like these things, like they are going to change different way. Okay, stress on the switches and all those things changes depending upon how you do the coupling. In some cases, you will find that transfer voltage is very regulated. So those are the characteristic of the impedance network, how you are going to form it. But this resonant for the resonant coupling, this is required. So you see that this compensation is there. So once this compensation is there, what? See this up to here, what we are seeing, this is called high frequency AC link. Naturally, it provides us this one. This part is ground, is buried in the ground, and this one is the with the vehicle. So this part is your high frequency AC link. AC link. Again, you have a high frequency rectifier and then onboard buck converter to submit charge into the battery. Anyone is having any doubt here? If you have any doubt, you can ask me right now. So these are some developments which are there in our lab with a wireless charger. This one, what you are seeing, this one, this is a active front-end rectifier. This is high frequency inverter, which is operating at 85 to 90 kilohertz. And this is a transmitting coil, like you can say a charging station. On the base, you can see a transmitting coil is there, and on the receiving coil is here, the vehicle. These are close picture, what you see. So this is your buck converter. This one is the buck converter, active front-end rectifier. This is the and this is the buck converter. This is the high frequency rectifier. These are some waveforms of transmitting and receiving side. Charging station. In charging station, we can have, you see, same conducting arrangement will be there, but multiple charging points can be there inside. You can have some algorithms, etc. charging station. It can be automated and scheduled also. Means only single central charger is there, and multiple vehicles are just connecting to it through the coils. Only the coils are there, not multiple power electronics is there. So in this case, we basically go for the pulse charging, and then we schedule that how much time this vehicle will be connected, for how much time this vehicle will be connected, and for how much time this vehicle is going to get connected, like this. Now, see, everyone wants that their vehicle gets charged at faster rate. Why? Because we do not have that much time, or we need to travel a longer distance. So in between, we are charging it. These could be the reasons. So what we do that we try to inject the current at higher rate. You remember that I said that CY10, okay, KCY10. So these 2, 4, 6, 8, 10, these are CY10. Now I am going to explain what is the impact of the temperature. Okay. So probably this is the last point I'm discussing with you. So here you see that when you charge at faster rate, what happens that you're going to, like, let's say this is 100 Ah battery. So 20 ampere you're injecting. So in 1 hour, you will be able to reach to 20% state of charge. And what the temperature rises? This much. Now, if you charge it continuously, then accordingly the temperature is going to rise. Let us consider that here, if you keep on increasing the rate, then what will happen? That let's say that you are charging at 8 CY10. So in 1 hour, you will be able to reach to 80% of SOC. But observe the temperature. But observe the temperature. Observe the temperature. This is 200 degrees. This is not allowed. We lose the battery. So the maximum allowed temperature during the charging process is 50 degrees Celsius. Okay, 50 degrees Celsius. And when you discharge your vehicle, it can go maximum to 60 degrees Celsius. So this is the basically limitation. So whichever battery characteristic this one is there, you can see that the temperature 50 degrees Celsius during the charging process is rising here. It is reaching here. So you can charge this battery pack with maximum of this one. This is something 3, means 3.5 C/10. Means this battery pack can be charged with 35 ampere rate continuously in 1 hour. And in 1 hour, it will reach to around the 35% of SOC. We cannot go beyond this one. Why? The temperature is reaching to 50 degrees Celsius. So then what we do? You have to make some cooling arrangement or stop it to cool down. Or let's say that there's another battery technology whose temperature rise rate is something here, 7 to 8 C/10. Okay. So 7 to 8 C/10, like is case of lithium ion battery. This is 7 to 8 here. So you see that when you charge it at 7 to 8 C/10, like here you see that in 1 hour it reaches to around 80%. This is what everyone says, that in 1 hour 80% charge. And by this time, how much is the rate of this? 50 degrees Celsius only. So basically, this at what rate temperature is going to rise and how much current you can inject to have the same temperature rise. This is decided by the thermal time constant of the battery. The lead acid battery are having the lower thermal time constant, and lithium ion batteries are having higher thermal time constant. Okay. So that's why you see that in case of lithium ion battery, we generally prefer the lithium ion battery because we can inject a higher current to the battery and get the battery charged in 1 hour with the limitation of this 50 degrees Celsius. So then why we are talking about the temperature? Thing is that, sorry, temperature plays an important role in deciding the life of the battery. Okay, how? You see here that operating temperature is this one and expected life month is this one. So you can see here that operating temperature is 20 degree, 30 degree, 40, 50, 60, 70, and life is 60 months up to 5 years means. Now, let us consider one case. We have a battery and we are charging it and the temperature is to the maximum allowed. Let's say that charging time of that battery is, let's say for an example, 4 hours. In 4 hours, we are charging our battery. And during these 4 hours, Nowhere the temperature is crossing 50 degrees Celsius. So 4 hour means what? 4 multiplied by 50 degrees Celsius charging time. Now let us consider that we are discharging the vehicle and we are able to discharge the vehicle in 2 hours. Maybe in 2 hours you run at 50 kilometers per hour, so you travel 100 kilometers. So maximum temperature allowed is what? 60 degrees Celsius. So 2 multiplied by 60. So this is 6. How much it is? 200 plus 120 divided by 6. So this is 320. How much it is? Around 53 degrees Celsius. Okay. Where is 53 degrees Celsius? Can you see? This was 55, 53 degrees Celsius. So here you see that you are going to lose your battery in about 1 year. It's a problem. So let us consider that the various possibilities are there. We can make the cooling arrangement. Let us say that while cooling, operating, we are maintaining a temperature of 50, let's say that 30 degrees Celsius by some cooling arrangement. And again, in 4 hours, we are getting charged. And then 2 hours getting discharged. So how much time? 6. How much it is? 120 plus 120, that is 240 divided by 6. That is 40 degrees Celsius. Where is 40 degrees Celsius? Is it? How much? 20 months. So the same battery can live for a longer duration of time. I mean, longer years service life is there. So in first case, it was 10 months. And when you ensure the temperature regulation to a lower temperature, let's say 30 degree, so your battery is going to average operating time. I'm saying about you can extend the battery life, see, 10 months to 20 months. So that's why the cooling arrangement is very, very important for the extended life of the battery, whether it is charging duration during the charging or whether you run your vehicle and with the help of cooling arrangements like change materials or heat pipes, whatever that, you are also cooling the battery by ensuring the temperature is lower. Okay, so these are all from my side. So anyone is having any doubt, you can ask me. Any question?
Participants can ask any questions.
Good morning, sir. This is Ashish from Bangalore.
Yes,
Sir,
Ashish.
I want to ask one question related to this charging simultaneous behavior of battery charging and discharging together. So, sorry. Sir, when we talk about charging and the temperature constraint that while charging the battery of the electric vehicle, when we talk about this pulse method, where at after a certain period of time that you showed in your graph, that for example 40 degrees Celsius is the temperature for a particular hour of time.
Okay.
How to design this concept in terms of I'm thinking about charging my battery for some time, and then
Okay.
for a short duration of time I want to discharge that, so that the overall temperature of my battery should not exceed the restricted limitation of the temperature, and obviously my lifetime of my battery should also improve. So as you have shown, previously it was 10 month, and after that it was showing that the battery can go for 20 months of time. So during design constraint or while writing a research proposal, how to think in that direction, sir?
Say, when we talk about reason charging arrangement, so basically when we were carrying out research on this one together with my student Sadhya Laviti, so we try to understand the behavior of the battery. So what we did that we set a temperature rise and temperature reference, and we started increasing the current, charging current. Like you see that this is on 26 Ah battery pack. So when the normal charging was there, so nowhere it was reaching to the set temperature. So it was the continuous current charging. So when we do the continuous charging, with the increase in the charging rate, charge submission increases. Okay, but
Okay.
now if we increase the charging rate beyond a particular limit, and what that limit is that by this way, with that limit, as you see that now it's 2.6, it is bit faster, 4.55, something 5.
1.5. Yes.
So what happens that our temperature is reaching to the maximum limit. Okay, so you have to stop charging. Then again, when it goes below, then a particular reference, then again you start charging. So this is turning out as a pulse. So this can be realized by what? Maybe a hysteresis type of arrangement. You set upper band and you set a lower band, or you work with a predictive arrangement, looking into the all the battery temperature and other constraints which are to be respected during the charging process. So like you see that when we go for the charging and this regulation, automatically you observe that with the increase in the charging rate, this is getting down. And this process is getting down. Are you able to see? The charge
Yes. Yes.
submission is
Yes.
getting down. But
Down.
which
Yes.
is our constraint? We should not go below the normal charging rate, that is C by 10. So we are operating in this region, region B, but this is in our hand. The temperature of the battery cut is in our hand. So you see that we can play with this region. What we have done that we have given a shift in the temperature reference. What we can go maximum 50 degrees Celsius. So maybe like you can work with 48 degrees Celsius. But in each case, temperature is in your control, and we are able to ensure the faster charging rate. So with a lead acid battery, we were able to charge it to maximum 3.75, and then we were able to demonstrate it in 4 hours, some minutes, 15 minutes, something, in place of maximum charging time of just 10 hours. But the benefit what we have seen here is that, you see, that state of health of the battery, if you ensure the temperature regulation is better as compared to the constant current, constant voltage charging. This is one
Yes.
thing. Then
Yes.
here is number of cycles if you are operating with, and this is also better when you operate with the temperature regulation. Means that doesn't matter that you give the temperature regulation just with the same temperature control strategy. Maybe some external arrangement, cooling arrangement, etc. are also being used. And what we done that we have said that in both the strategy, CCCV and temperature regulation, both are reaching to the constant same state of charge SOC level at the same time. So with this, we made the control. So in one case, it operates at 37 degrees Celsius average temperature, and in another case, it operates at 53 degrees Celsius temperature. So you see that we have that plot. If it is operating at 53 degrees Celsius, where it is here, 53, we are here. When you are operating at 37, so 37 is somewhat more. This is 37. Huh? This is this
Yes.
is this is 35. 37 is somewhere here.
Okay. Mm.
37. So this month we are getting where 53 degrees Celsius means what? This is 55 somewhere here. So this much of improvement we are able to observe if you just make the cooling. So this is the difference. 30 months and this is 10 months. So this is for lead acid battery. The lithium ion batteries even in a better way we can say. Okay.
Okay. Okay, sir.
So
So, yeah.
yes, just give me something. So to
Uh,
do this one, you have to design your own temperature regulators or these things like we have made electrothermal aging models, etc. So based on this, we made our own temperature estimators. I show you. These things thermal because we do not have time to discuss. We have a temperature estimator which in which we have a what we say the system identification arrangement is also there, with which we are able to measure the battery parameters and update it regularly. Okay, this one. So we have used these algorithms of temperature estimator to ensure the temperature regulated battery charging. Okay,
Okay,
so this
so
is
that's
so you
why
must
I
have some
wanted to
algorithm.
yeah, I
Uh,
wanted to see based on we got the response, but in terms of like starting from beginning, like in the terms of designing process and how
uh,
steps were formed. So now I can actually correlate, like first we have to
yes.
design a model and then we can go for these
Yes,
changes.
we have to rely on this electrothermal model. Then, if it is better, you incorporate SOH update also. if it is better, you can use take the help of system identification and update the battery parameters regularly so that your temperature estimator should be always updated and synchronized with the actual battery. So and so this is a basically this is a low cost solution and which gets our helps our work done in a proper way. And other thing is that directly you incorporate a sensor, temperature sensor, like which is mandated now with lithium ions. So then we can work.
Okay, sir. Okay, sir.
This is what.
Thank-
So
Yeah,
in any
thank you
question?
very much, sir.
Thank you.
Thank you
Yeah,
very
thank
much.
you. Anyone else is having?
Sir, excuse me, sir. I'm from Itanagar, Arunachal Pradesh,
Yes,
Northeastern
brother.
Regional Institute of Science and Technology, sir. Myself is Radak. Sir, actually, a nice lecture, sir. Actually, I'm also working on this electric vehicle in my department, electrical department. Sir, just
That's good.
sir, what is the minimum and maximum switching frequency you use in the MOSFET, sir?
Now, for what? So this is a big constraint, basically. That minimum and maximum switching frequency is decided by two things. One that if
Okay.
you see the data sheet, some losses are mentioned there.
Yeah, yeah. Okay, okay,
Okay,
okay,
so
okay,
you
okay.
have
Yeah,
to
yeah, yeah.
respect that loss
I'm getting,
only. But you can
I'm
definitely
getting now,
work with proper ZVS and ZCS solutions, which will help you
sir.
to operate with very high frequency also. So basically, what happened when we were working with wireless charger, so we were chopping 30 ampere of current at 85 kilohertz. So at the beginning,
Okay,
we
okay,
worked with
okay.
MOSFET also, IGBT, then
Yes, sir.
MOSFET. So all were getting fire. So then we worked with some like impedance arrangement method for the coil system.
Sir.
And then we also moved to wide band gap device, like that we prepared this silicon carbide. So the two solution together helps us in making our system thermally stable. But the main challenge is that if we can do the same thing with normal MOSFETs, then it will be so nice. So we are actually working with this. And the reason is that
Okay, sir.
one SIC switch you get at around something 8,500 rupees something. So if you make one H bridge, so you can see
Okay, sir.
that around 33,000, 34,000 cost is there. But if you do the same thing with a normal silicon MOSFETs, and the cost is around 300 rupees. So you can see the
Okay.
difference. In one place,
Yeah,
1,500
sir.
rupees.
Huge difference, sir.
So this is a research point which is there, and
Okay,
this
sir.
should be realized. And if we realize it properly, then for solutions like wireless charger, we will be able to reduce the cost drastically.
Thank you, sir. Thank you, sir.
Uh, Yes, so you have to see the
Thank you, sir.
switching losses and the impedance arrangement method. Like different
Okay,
different
okay, sir.
topologies
Okay.
are there, which will help you in reducing the losses, switching losses.
Okay,
So
sir.
you will
Okay.
be
Okay,
able
sir.
to work to with this normal early technology silicon switches also.
Okay, sir. Thank you, sir.
Thank you. Any question?